let's see. So Jinhua gave me a title for this talk. He suggested the future of embodied AI. And I've decided to change this title. And in fact, I've decided to go to physical intelligence. Why is this not working? So I've decided to go to physical intelligence or physical AI. So why the switch? Well, because while embodied AI in robotics is about making the body of the machine intelligent, like designing materials and structures that sense, adapt, compute, physical AI shifts the focus to the brain. And so with physical AI, we talk about AI systems that don't just rely on statistical patterns the way transformers do, but that reason, act, and learn in a way that respects the physical world. And so you can think of this as going from muscle memory to physics-aware cognition. And so, in short, we're not just giving machines a body; we're giving machines the brains that play by the rules of nature. And so, this is exciting. It's a very special moment to be talking about physical AI or physical robots, which to me means increasing the brain capabilities of machines like robots by using AI's power to understand digital text, images, and other online information. And really, this is synergistic with embodied intelligence, which concerns how the body or the hardware of the robot adapts to its environment in an intelligent way. And so physical AI is about making the brain of machines intelligent, and embodied AI is about making the body of the machine intelligent. And why are we interested in this? Well, today in the field of computing, we have two largely separate fields. We have artificial intelligence and robotics. And AI is amazing us with its decision-making and learning, but it remains confined inside computers. On the other hand, robots have a physical presence and the ability to execute pre-programmed tasks, but they are mostly not intelligent. And so my objective is to bridge the separation because there are so many tasks in the physical world that operate according to constraints, to common sense and other physical phenomena. And so I want to bridge this separation by developing this field of physical AI. And so with physical AI, AI doesn't just reside inside computers, but it also interacts with us in the physical world. And so we cannot use digital AI directly to realize physical AI because of several things. First of all, digital AI has to be applied to very complex mechanisms which make up our robots and satellites and energy grids. And so, for example, one example of complex mechanisms is the humanoids. And humanoids can do really extraordinary tasks. And sometimes it works, but many times it doesn't work. And so the problem with controlling things in the physical world is that really controlling these mechanisms in a robust way is very challenging. The second reason is that AI lacks common sense. So I gave an AI system a simple task. Let's see if we can hear this. Over there? Oh, yeah. Sorry, so let me start all over again. Okay.
Can you water that plant over there?
Yeah. So I gave this AI system a simple task, and within its programmed context, it performed just fine. But if you change the environment, or if you ask it to do the same task in a new setting, or if you give it a related but unreasonable task, it breaks down. This is because today's AI lacks the ability to reason.
That's very good, Neo. Can you water my friend here? No, I was just kidding. Don't do it.
So today's AI lacks the ability to reason flexibly and understand the context. It does not have common sense. The other thing is today's AI makes mistakes. And it is challenging to use models that make mistakes on safety-critical applications, such as the ones with robots. And so, for example, this AI system is attached to a robot car, and it's very good at detecting individual cars and individual pedestrians. But when pedestrians come in clumps, it becomes unreliable because the structure is amorphous, and unlike other things that it has seen in its data set. And so for physical AI, we need brains that do not make mistakes. For physical AI, we also need software that can run on small computers on the body of the machine. For example, this is a robot fish. Well, today's AI doesn't fit because it requires server farms. In other words, every GPT or every large language model chat you put out there in the world requires a cloud. It requires the connection to the cloud, and the answer is delayed depending on your network connection and what happens in the cloud. For physical AI, we need real-time performance. Also, AI has a very high energy cost, which cannot be covered by onboard batteries. So here in this chart, you see the 2030 projection of the fraction of U.S. power demand that is taken by U.S. data centers. 12% is a lot of energy. And Eric Schmidt recently said that we're on a path to completely exceed all the energy sources available on Earth using AI systems. So we have to do something different. So let me take a minute to explain why this energy cost is so important. Today's very large frontier models like the GPT models or Claude or Gemini are really huge models on the order of trillions of parameters. And they're built in two very energy-intensive phases called pre-training and fine-tuning. And the goal of pre-training is to have the model learn the general knowledge embedded in the data. That means the more knowledge you provide as input, the better the model. And so large language models end up being trained between 1 and 15 terabytes of data. And they're trained to learn the weights in a transformer architecture so that they can generate sentences, so that they can do next token completion. For example, after pre-training on many facts, the model can say correctly that the first robotics summit was held in 2018. And then the second phase, fine-tuning, uses specialized data to adapt the model to do useful applications downstream. For example, to follow instructions. And here's an example where you're asking the model to summarize. Both pre-training and fine-tuning are energy intensive. Training a model is very energy intensive, but because we end up with these huge models, we also end up with very energy intensive inference. But as I said, the more data we provide into the transformer model, the better the model. And so there's this belief that we are just going to continue to scale up, and eventually we will have the whole world's knowledge embedded into this transformer architecture, and therefore we will have all the intelligence in the world. So there are a couple of problems with this. First of all, transformers are feed-forward memorizers. If you read the famous transformer paper, "Attention is all you need," the third or fourth sentence in that paper says, we remove convolutions and recurrences in order to enable fast parallelism. And indeed, they have enabled fast parallelism, but the end result is a feed-forward structure without inference, without learning from the past. And so therefore, we end up with a very statistics-centric model, which does extraordinary things, but in some tasks, we actually do want to be able to learn from experience. The second problem is that we are beginning to show how scaling impacts the model performance. And we are beginning to see diminishing returns of scaling. And you can see this S-curve, which is the performance of aggregated models on a number of so you see a number of models that are being tested, and this performance is on a challenging benchmark called the MMLU Pro benchmark. And so this is raising an important question. Are there new ideas that will not make mistakes, that will result in small models that can fit on robot bodies, and that will lead to better performance over the transformer-based architectures? And so in our group, we are using inspiration from a worm called C. elegans to answer this question. Now, in stark contrast to the billions of neurons in the human brain, the worm lives happily on only 302 neurons. And biologists understand exactly how these neurons work, what operations they perform, and how they are interconnected. So here's the idea. Can we use the math of the worm neurons to build a new class of AI? And we have done so, and we have called this class liquid networks. And these liquid networks are compact, provably causal, and explainable as compared to today's solutions. Let me explain. So this is our MIT self-driving car. And this car was trained using a traditional AI solution, the type found in many applications today. And it was trained by using visual feedback and by looking at how humans steer and accelerate based on this feedback. And here's the dashboard of the car. In the lower right corner, you see the map. In the upper left corner, the camera input stream, and the big box with the blinking blue and yellow lights is the decision-making engine which tells the car how to steer. This decision-making engine has on the order of 100,000 neurons, and it is impossible to correlate how the neurons fire with the behavior of the car. And furthermore, if you look at the lower left corner, this is the attention map. This means where in the image the decision-making engine looks in order to make mistakes. And you can see that the car stays on the road pretty well. But the attention map is very noisy. It's focused on the entire image and also primarily on the bushes and trees on the side of the road. Now imagine how you would drive if your attention was on the bushes and trees of your road. So this is not how people drive. People look at the road. So we can conclude that this is a pretty good solution. We don't understand how it makes the decisions. It keeps the car on the road, and it tends to look at the context of the task. Now contrast that to the worm-inspired liquid network for self-driving cars. This solution uses only 19 liquid neurons instead of the tens of thousands. And look at how clean the attention map is. And look at how it is focused on the road horizon and the sides of the road at the horizon. And I would argue that this is how we drive. And in part, this is because with liquid networks, we have a provably causal solution. In other words, we have a solution that understands the task rather than the context of the task. So how is this performance possible? Well, in most traditional AI solutions, the artificial neuron is an on-off computational unit. It takes in some numbers, it adds the map, it passes the solution through some basic math, and it puts out a 0 or a 1. And this becomes complicated because it's a computation that's happening across thousands of neurons. Liquid networks use fewer neurons, but each one does much more complex math. They're not simply on-off solutions. So here we use the math of we use inspiration from the math of the worm for the synapses and also for the computation of the neuron. And so you see the two differential equations when we plug them into. You can just use it. Yeah, it would. Okay. So when you plug these two equations, when you plug these two equations into each other, you get this equation, which is what the liquid neuron puts out. And so it's a differential equation with a very special structure. So notice that typically in a differential equation, you have x of t, and you have a constant, the time constant that goes in front of x of t. Well, here what do we see? We see that this time constant is not really a constant. It depends on x of t. This is what we call it liquid. Initially, we called them liquid time constant neural networks. That seemed like a mouthful, so we dropped the time constant. But it's because of this. And also because of this mathematical formulation, we get very interesting properties. We get adaptation. In other words, these AI solutions are able to learn after training. They adapt after training based on the inputs that they see. This equation so these networks are also very energy efficient. And now you should be asking, how can they be energy efficient? Because differential equations require this energy guzzling numerical integrators to solve. What's really exciting about this equation is that it has a closed form approximation with a very good upper bound. And so that means we don't need the integrators. We can just plug this equation into the neurons, and it's a kind of a straight up computation. It's pretty hairy, but nevertheless, it's not expensive. So we also wire our neurons differently. In the worm, the neurons are not all identical. So we have motor neurons, command neurons, interneurons, and we have the specialized architecture. And then we have loops in this architecture, unlike in transformers. And so with these changes, we have some extraordinary benefits because most of today's solutions are frozen after training. That means you deploy them in the wild and they don't change. If you need some changes, you have to wait for the next release. Now, because of what's happening inside the liquid neurons, these solutions adapt after training based on the inputs that they see. And so I'll show you an example. And so we trained a lot of models, AI models and liquid networks, to find things in the woods during the summer. I guess I will note that in Singapore it's always summer, but in Boston sometimes it's summer, and then we have other seasons. So we trained in the woods using videos like these ones. The videos are unlabeled, and interestingly, all the models learned how to do this task. Then we tried the model trained with data from the summer during the fall. And here's the standard solution. The drone gets confused by the background because now it's fall time. The leaves, the background doesn't look like it did in the training data. And so the drone cannot solve the task. But check out the liquid network. So the liquid network continues to perform well. It sees the object, it locks into it, and because it's causal, it completely disregards the background. So the solution also works in the winter, and you can bring it from the woods to an urban area, and you can even manage dynamic objects even though you trained on static objects. So you have a lot of adaptation because these solutions learn skills. And so I believe that liquid networks are important because they get machines to think using this kind of physics-based technology for AI. And because the models are compact, they can run on smartphones, on robots, on enterprise computers, on sensors, on edge devices in general. Now, one limitation is that these liquid networks require time series data. We have a lot of applications from sensors, from financial transactions, even text you can think of as a time series data because words come one after the other. And so we did some direct comparisons between liquid networks and transformers. I know you can't read the table. I just wanted to put it there so you could see that there is a lot of experimentation. And for instance, we got 123% improvement over transformers in physical real-world dynamics modeling. We also had better performance on information retrieval, log list operations, text sentiment analysis, sequential image processing. And so this is very exciting. Next, we built foundation models using this technology. And so here you can see a comparison between 1 billion parameters liquid foundation models, 3 billion parameters liquid foundation models, and 40 billion parameters liquid foundation models using only 12 billion parameters that are active. And so you can see comparisons between these models and the state of the art in that category. And I would like to call your attention to the 40B or 12B model and check out how it's like even higher, better performant than Llama 70B. And I should tell you that the LFM 40B was trained on 300 GPUs. The Llama 70B was trained on 50,000 GPUs. And so this kind of technology, I think we can really begin to imagine bringing AI closer to machines, getting AI to be less energy guzzling, getting AI to be much more manageable for sustainability. The other thing that's interesting about these models is that their memory footprint is low. And so here you can see the memory footprint of liquid 3B, of the liquid 3B parameter, as compared to everyone else. And because of this low memory footprint, we end up with compact models that can run on your phone, on your computer, on a satellite, on an energy grid. And so this is really exciting. Also, the fact that we can bring together multimodal data in liquid foundation models gives us another advantage. It allows us to connect sensor signals with language. And this is very interesting because this allows us to think about how language contributes to intelligence. Now, when we deal with a physical world in a robot, we usually think about pixels or XYZ coordinates, which are very difficult for people to conceptualize, for humans to conceptualize. Language allows us to raise the level of abstraction and reasoning that is possible for intelligent machines. And let me give you an example. So say you have this image and you have some text describing it. We can build a foundational model that aligns the perceptual features and the language features in the same latent space. And then we can train models to control relative to some concepts. For example, we can train a model to avoid a deer using video training data. And then, using language, we can say it in words. Now, also avoid animals and trees and cars without using the training data. So in other words, we obtain out-of-distribution generalization at the level of abstract concepts that enable people to connect to the task of the machine, because what we're learning with liquid networks is the skill. And then we can map the skill into everything else. So let me show you pictorially how this works. Essentially, we simulate latent features by swapping some image features with textual features. And so essentially, for each patch, we identify the closest textual features, and then when we have to apply the skill to a new environment or a new task, we essentially swap the features. There's no more training needed, and this swapping operation is very efficient. So, in other words, the policy now doesn't see image features; it sees text features. And so here is an example that shows how well this works. So we have zero-shot out-of-distribution generalization from training to avoid a car in the woods. Now in words, we can say now also avoid all these other objects. We can also go from that initial training data to many other environments where you may have different environments, different luminosity, different seasons. And so this is really exciting because now, as I promised you, I have a model that understands physics, that runs on your device, that can run on the robot, and that is capable, that can be generalized to a lot of tasks. So that's the first thing I promised promised you. I also promised you that we can, or at least I told you that we're challenged because AI makes mistakes. So now that we have capable, compact AI, the question is how do we ensure that it does not make mistakes? Because frankly, because of all the uncertainties and the errors that exist in physical tasks, we are going to observe mistakes. So the idea is actually quite simple. What we do is we marry machine learning with control theory. So we take our machine learning model and we add a layer to it that is called the control barrier function. And control barrier functions in control theory essentially put safety conditions into math. So if we take our model and we can put the safety conditions into math, essentially we force the output of the model into a safe region. And so then with barrier net, we can ensure that our control solutions are fine, even if we have uncertainty in sensing, and we can even give Tom Cruise an AI system to fly his plane in the canyon like he did in the movie Maverick. So this is very exciting. So what I told you essentially is that we can change how machines think by developing these physics-based machine learning solutions. And since we're talking about embodied intelligence, I wanted to also connect how we can actually think about the body, how we can increase our ways in which we can specify and create new bodies. So by now, you are probably used to generating images from text. For instance, I was very interested in a research concept. I asked GPT if it could help me with a research concept of a robot that can pick delicate fruit. And these are some of the samples of what we got. Now, I have to admit that these are very creative and cool ideas that combine robots and fruits. This is my favorite. So if you look closely at this design, you see that there are many physics aspects of the world that are not captured here. First of all, the stem on the top seems to defy physics since it is thin and seemingly very brittle. And moreover, if you fix both ends of the gripper onto this strawberry thing, how are you going to even manipulate? You actually don't have an actuatable structure, and then the surface is very challenging to fabricate. So it's not possible to use today's AI solutions to do design of embodied machines because they do not understand physics. And so instead, we developed an AI solution that guides the design process by checking and simulating the physical requirements. And so you start with a simple language statement like, make me a robot that can walk, and our system generates the design, including shape, materials, actuators, sensors, even the programs required to control this device, and the fabrication files to make it. And it does so by using a physics simulator to check the results that come from the design generation. And this physics simulator is then used as a signal back into the generation process along with optimization. So the first concept might look like this. The second concept might look like this, which is a much more efficient leg-like thing. And we even accelerated the process, and eventually we got this walking teapot, which I thought was pretty interesting. We can use the same pipeline to design a robot that can pick things up. And then we can do more. We can connect this design process into agents that will go out there in the world and look at all the design documents and the papers about this idea, and will then use this prior knowledge to come up with new designs. I'll just show you some examples. So this is a complicated process, but it's basically a multi-agent search of all the literature on design. And so if we connect that search into some existing modular parts that we can compose into new designs, we can get this system to automatically design different kinds of manipulators. So this is a design for manipulating a syringe. Notice 2 fingers and something that pushes. This is a design for operating a pipette. So now we have the holding fingers and we have the squeezing fingers. We also have a design for pliers, and we have a design for operating a drill, which means we have to do a different grasp, and you have to have a button to push that. To push the syringe. So with this approach, with AI applied to design and with AI guiding design in a kind of a physics-centric way, we can generate machines, we can generate designs that meet physical constraints. And so I want to take just a minute to say, to show you one more thing. So we have now AI that can get machines to think in the physical world without mistakes. We can design these machines, and now we can even get these machines to learn from humans how to do complex tasks that cannot be modeled from first principles. And so here's how it works. In our lab, we created a laboratory for kitchen tasks. We instrumented people with sensors, and we record pose, muscle, even gaze when people perform kitchen tasks. And so we really need physical data, because video alone cannot capture the dynamics of the interaction. You do not get forces and torques from videos, and these are important in manipulation. Okay, so then we use liquid networks to learn from this data how to get robots to perform those tasks, because liquid networks capture spatio-temporal correlations. And so the end result is machines that move with grace and agility, as well as adapt and learn, which is really physical intelligence. This process can be generalizable to lots of other tasks. So here's a very slow movie that shows the first step of making lemonade. And in the interest of time, I'm going to skip this. But the point is that you can actually compose skills into multi-step processes like make lemonade. And you can do so by watching humans how to do these tasks, because these tasks are not modelable from first principles. So we can teach robots to do food preparation, cleaning, and so much more using data from people. So the ability to turn photos into words and photos and words into functional machines, coupled with liquid networks to create powerful brains that can learn from humans, is incredibly exciting, because it means we can build almost anything we imagine. Today's AI has a ceiling. It needs server farms. It has a high energy cost. It makes mistakes. When new AI ideas enable AI to move into the physical world, we will have incredible breakthroughs and benefits. We will have personal assistants that optimize our routines and anticipate our needs, bespoke machines that help us at work, and robots that delight us in our spare time. So the promise of physical AI is to transcend human limitations with capabilities that extend our reach, amplify our strength, and refine our precision, and grant us the ability to interact with the world in ways we've only dreamed of. And so physical AI demands a paradigm shift. It requires safe models, and emerging ideas like liquid networks can set us on a positive path in this direction. So thank you very much. The potential is really big. Thank you very much.